There we go. Okay, today we talk about supermassive black holes. Let's get started. It should be a fun lecture. And Matthew, my day is going great so far. Beautiful day. Okay, supermassive Milky Way Galaxy and supermassive black holes. Before we get started, I have a public service announcement. Let me kill that. Mute all. Okay, public service announcement. I'm sure you've been hearing things about voting. Voting is actually more important now for you than it's ever been for you now or probably in the future. North Carolina, as you probably know, is a battleground state. So that means that your vote might actually affect the election. And the vote in North Carolina is fairly close. And this election is probably one of the most important that we've had. There's only been a couple of times in the history of the country where we had to decide fundamentally what kind of country we live in. One, of course, was in 1787. The other time, of course, is the Civil War. And I think we're at a third point now, an inflection point. So the most important thing you can do now is to vote. And one question you have to ask yourself, and this is more important for you than for me because I'm old, I'm not going to be around forever, but you guys will be. And you guys need to decide what kind of country you want to live in. And you need to answer yourself this question because you'll be asking yourself this question in the decades in the future is what will you do in the next month to guarantee that everybody gets a right to vote? So that's enough of the public service announcement. I had a question last time. Somebody noticed that there was an announcement of a black hole eating a star, which actually we've observed several times before, but this was a cute one. So here it is.
On January 21st, 2019, for the very first time, NASA's TESS saw a black hole destroy a star. This was a tidal disruption event, which occurs when a star passes too close to a black hole. Extreme gravity causes the star to bulge and break apart into a stream of gas. The tail of the stream escapes into space, but the rest swings around to form an accretion disk. This event, called Assassin 19BT for the All-Sky Automated Survey for Supernovae, which first identified it, happened in the TESS Continuous Viewing Zone. TESS's 4 cameras scan large sectors of the sky, and one constantly monitored this region for a full year. TESS saw Assassin 19BT as soon as it started to brighten, days before other observatories spotted it. NASA's SWIFT satellite quickly observed the outburst in visible light, UV, and, along with the European XMM Newton satellite, X-rays. The UV measurements are the earliest recorded for a tidal disruption to date. They showed the event's temperature dropped almost 50% in just a few days. Such a steep decrease has never been seen in a tidal disruption before. These outbursts are rare, happening only once every 10,000 to 100,000 years in a galaxy like our own. Future discoveries will help us learn even more about these uncommon cosmic blasts.
Okay, so that's talking about a supermassive black hole eating a star. We haven't mentioned supermassive black holes so far, but we will today in today's lecture. Just for the sake of reference, this happened in a galaxy that is 215 million light years away, so relatively close as things go. And the black hole had a mass of 6 million solar masses. We'll relate that to other supermassive black holes later in this lecture. So this is very illustrative. Also, when a black hole eats a star, typically about half the star is spewed out into intergalactic space, and the other half is swallowed up by the black hole. That turns out to be very stereotypical, that you swallow half of it and the other half is escaped. you almost have to do that so you lose enough angular momentum for the rest of the star to be eaten. Okay, so when we say the term Milky Way, and assuming you don't live in North Carolina, this is usually what people think of. They think of this bright band of cloudy stuff, milky stuff in the sky. And so typically the way astronomers talk is when they say the Milky Way, what they're referring to is this bright band of clouds, as opposed to the Milky Way Galaxy, which is the object that created that bright band. So wouldn't it be nice if we had skies clear enough and dark enough we could actually see this with the naked eye? Okay, so Milky Way Galaxy is the faint band of light that we call the Milky Way. Uh, Not to do a spoiler here, but that band is the galaxy that we live in. And we believe this is what the galaxy that we live in, we believe that this is similar to the appearance of the Milky Way Galaxy. So how do we know we're in a galaxy? What's the size and the shape of the Milky Way Galaxy? You often see me use MWG to stand for Milky Way Galaxy because I have old fingers. It takes a long time to type. How do the spiral galaxies that form the Milky Way Galaxy? The Milky Way Galaxy is what's known as a spiral galaxy. The term is not terribly imaginative because this is what they look like. What's the mass of the Milky Way Galaxy? And then we'll talk about the supermassive black hole at the center of our galaxy. Well, how do we know we're in a galaxy? This was a real challenge. The challenge was that we see this band, and the band tends to be relatively uniform all the way around our view. And so what William Herschel thought was that we were in this disk, and the sun is at the center of the disk. He was not aware that the reason it looks relatively uniform all the way around is because towards the center of the Milky Way Galaxy, gas and dust really inhibits our view of that. And so that's why it looks like we're at the center of this disk, but in fact, we're way off into the edge. Okay. So we need to be able to figure out what the size and shape of it is. And we had to do that with a couple of special stars. One is what's known as variable stars. And we've mentioned this before, our Lyrae and most importantly, Cepheid stars, they oscillate, and the speed of the oscillation depends on how bright they are. So if you can see how fast they oscillate, that will tell you how bright the star really is. And if you know how bright the star really is, and you know how bright it appears, those two facts can tell you how far away the stars actually are. So it's a great way of measuring distances. And Cepheids in particular are very bright, so you can see them very, very far away. Another thing are these big clusters of millions of stars called globular clusters. And globular clusters were visible all around, not just in the plane of the Milky Way. And so what was interesting about the globular clusters is some of these globular clusters actually contain Cepheids. And so we could measure the distance to these Cepheids. And when we did that, we discovered that these globular clusters tend to cluster on one side around what we now know as the galactic center. And I'll show you that in a few minutes. And so by using variable stars and by mapping these globular clusters and assuming the globular clusters surrounded the center of the object that we were embedded in, we were able to calculate the distance to the center of those globular clusters. And using these Cepheids and our Lyrae stars, we were able to calculate the distance to them. And that gave us the size and the shape of the Milky Way galaxy. So this sounds complicated, and it was. And so it took a long time for us to figure out that we were embedded in a galaxy and what was the size of this galaxy. So here is the picture. This is the best picture we have of the Milky Way galaxy. We're in a spiral galaxy. We're actually, and this is just recent in the last few years, we now believe we're in what's known as a barred spiral galaxy. A barred spiral galaxy is where the nucleus isn't spherical. The nucleus is elongated like this in terms of a barred spiral. And we're, about half to 2/3 of the way out. We're in not quite the suburbs. We're kind of in the exurbs, not really in the rural area. And we're in this particular arm. I think it's called the Orion arm. Okay, so we're nowhere near the center of the Milky Way galaxy, which is good, because if we were at the center of the Milky Way galaxy, we wouldn't be here because life could not exist. The radiation level is just too high. So there we are. And if we're too far out, there's just not enough material to form planets. So we're kind of in the Goldilocks zone in terms of the location that we are in our galaxy. And we believe that's going to be fairly true if we're looking for life. So what's the size and the shape? We've got the things that you're going to be responsible for is we've got the central bulge. That's the technical term for it. We've got the disk of the Milky Way galaxy. And then we have this halo that contains the globular clusters. And I'll show you those in a minute. So the disk is very thin. It's flat. It contains most of the gas and dust. It's the site of all the action. It's where stars are formed. The central bulge is very bright. It's where the supermassive black hole is. Stars are extremely tightly clustered there. It's kind of a nasty place because stars are whizzing by and at very, very high radiation. And then this halo is, as we'll talk about in a little bit, it's what's left over from the formation of the Milky Way galaxy. So there's two types of stars that you need to know about. One is called population 1, and the other is known as population 2. Population 1 stars are the stars that are the stars that we're familiar with. Population 2 stars are older stars, meaning that they were formed at the very beginnings of our universe. Of our galaxy. So population 1 stars contain a lot of stuff. They contain a lot. Now, astronomers again use terms in unfamiliar ways. Astronomers use the term metal to refer to anything other than hydrogen and helium, which is kind of a perverse use of that term. But population 1 stars, which are in the disk, have a lot of metals. They have a lot of metals, meaning stuff other than hydrogen and helium, because they're several generations from the original creation of the universe and the original creation of the galaxy. Our universe was born with only hydrogen and helium. So anything other than hydrogen and helium was created in the guts of stars, in the guts of small stars that spew their guts in planetary nebula, in the guts of large stars that spew their guts in supernova explosions. And so when stars form much later, they form stars that contain hydrogen and helium, yes, but also contain the debris of these previous generations. And those are what we call population 1 stars. Population 1 stars are formed from the detritus of previous generations, as our star did. If we were not population 1, we wouldn't be here because there wouldn't be enough metals such as silicon and carbon and iron and all the good stuff that make up the Earth around to form planets like ours. Population 2, and again, I really hate this term population 1, population 2, because it's kind of inverted from what you think, because population 1 isn't a later generation, it's the current generation of stars. Population 2 refers to the first stars that formed in our galaxy. And they formed primarily from hydrogen and helium, because that's all that was around. And what's interesting is the disk stars are population 1, meaning they've got a lot of metals and they've gone through multiple generations. The halo stars that are in that big galactic halo around our galaxy are typically what we call population 2, no metals, which means they're primordial. They were formed originally, not from the guts of previous generations. Okay. So here again, our sun, there's the central bulge, there's the disk, and there is the halo. The globular clusters, typically the stars in the globular clusters are population 2, and they're very, very old. The implication is our galaxy used to be spherical and then it collapsed to a disk. And the halo and these globular clusters are what's left over from the birth of the Milky Way Galaxy. And the numbers tend to work out. So the halo and the globular clusters typically are about 12 billion years old. And that's about when we think the Milky Way Galaxy was formed. And remember, our star is only 5 billion years old. We're relative newcomers. So let me switch over and show you what I mean. Okay, so here's our galaxy, the Milky Way Galaxy. There is the sun. There is the central bulge. And notice it's very flat. Let's bring up some regions. Okay, so there is, let's bring up all the regions. Okay, so here's the definition of the regions. There's the disk region, there is the central bulge, and this red sphere represents the halo. And let me show you what's in that halo. So let's go to globular clusters, show all of them, and you can see the globular clusters that we've observed. They don't cluster around the sun. What they do is they cluster around in that big halo and really represent the original spherical proto-Milky Way galaxy. Okay. Got it? So let's go back. So the question is, this is very confusing in terms of coordinate systems. Does the Milky Way band follow the celestial equator or the ecliptic? So let me bring up another program. And this is very confusing. There's really 3 coordinate systems we need to worry about. So let's bring this up, new share. Okay, well, that's not exactly North Carolina. So let's options. Let's change it so it's not daylight. And let's advance time. Let's do 300x. Okay. So here is the stars as they're moving around. And let's show the grid. And so this is the coordinate system that we typically use when we're discussing stars. This is the what they call alt-azimuth coordinate system. And this coordinate system revolves around the North Star. And you can see there's the Milky Way right there. Let's see if I can show the constellations. There we go. So there's the there's the Big Dipper, there's the Little Dipper, there's the North Star. Okay. So the entire sky, if you're able to look up at the night sky, it revolves around here. And this is the coordinate system that for us on the Earth, it represents the night sky. Okay, so let's get rid of those. Next, and let's show the planets. Where are the planets here? Show the labels. Okay, so there's a minor planet that you can see there. Let's bring this down a little bit. There's the moon. And what I'm going to show next is the ecliptic. And the ecliptic, which we can't see, there it is. There's the ecliptic, that green line. The ecliptic, remember, is the line that represents the plane of the Milky Way. So that plane is where all the planets orbit. That's where the sun orbits. That's where the moon orbits. And you can see here, Saturn, Pluto, Jupiter are on this plane. And this plane is not oriented relative to the plane that we see. In fact, the tilt between this coordinate system and that coordinate system is 23 degrees. And that represents the tilt of the Earth relative to the plane of the solar system. And so our axis doesn't point straight up and down. Our axis is tilted 23 degrees relative to the plane of the Milky Way Galaxy. And that, as we've talked about in previous lectures, is the genesis for the seasons. So that's coordinate system number 2. So coordinate system number 1 is the coordinate system of the sky for us. Coordinate system number 2 is the coordinate system of the that represents our solar system. And we can show you that as a grid. Okay. So there's the coordinate system that is solar system specific. There is, unfortunately, a third coordinate system. And the third coordinate system is the coordinate system that's this purple line that represents the plane of the Milky Way Galaxy. Okay. So we have the orientation of the Earth relative to the sky. We have the orientation of the solar system relative to the sky. And we have the orientation of the Milky Way Galaxy relative to the sky. And all three of those are different. And so we actually have 3 different coordinate systems: the Earth-centered coordinate system, the solar system oriented coordinate system, and the Milky Way oriented coordinate system. And if I could bring up the, let's see, let me bring up the visibility of the Milky Way Galaxy. So where is that? Solar system, stars, constellation. Huh. Milky Way, there we go. And let's bring up, make sure that Milky Way is really bright. And let's get rid of the there we go. So there's the Milky Way Galaxy, as you can see. I mean, the Milky Way band that goes along there. Options, stars, Milky Way. And there we go. That's what I wanted to show. So there, I've increased the intensity of the Milky Way so you can see it better. And that's what it looks like from the Earth. Now let's go back to this. How far are we above the plane of the celestial equator? If you mean the equator of the Milky Way Galaxy, the Earth, I'm sorry, the sun is pretty much dead center. Okay, so here is the galactic plane. Here is the ecliptic plane. So imagine this is your solar system, and that's the location of the Earth right there. Okay, and so we have the galactic plane there. We have the ecliptic plane there, and then we have the celestial equator, which is the Earth-oriented coordinate system. So you can probably see it better on this. The most fundamental one would be the plane of the Milky Way Galaxy. Then we're tilted at 60 degrees relative to that plane. That this is the plane of the of our solar system, and then the Earth is tilted 23 degrees relative to that, as you can see there with the celestial equator. So it's confusing, but it is it is what it is. We just have these three coordinate systems, and you'll sometimes see people plot things on different coordinate systems. I've already showed you plots of things relative to the galactic coordinate system, but because plotting objects on the galactic coordinate system tells you whether they're oriented relative to our galaxy or over the entire sky. And if they're over the entire sky, either those objects are really close or very, very far away. Okay. So how did the Milky Way Galaxy form? Again, as you would expect from the halo and the globular clusters, we believe it started as a spherical ball of stuff. And then it started to contract just like a solar system does, except much, much larger. And there's these two hypotheses that are in the textbook. Really, what actually happened is almost certainly a combination of both. That, yes, it did collapse from a big spherical ball, but it also swallowed up a lot of additional objects. And we've seen even stronger evidence of that galactic cannibalism in just the last few years. And we've got some videos in the next couple of lectures that will show you that galactic collisions. But here we have this big ball of gas and dust. It collapses. And as we've seen in every object in the universe, when you collapse stuff, it starts to spin. And so you collapse into a disk and then it starts to spin. And here's the evidence we see when we look out at the night sky. We see evidence of the remnants of galaxies that were ripped apart as they were eaten up by the Milky Way Galaxy. These are called stellar streams. And you can see there's been a lot of these that have been identified just in the last few years. This will make a lot more sense when I show you the videos of galaxies colliding, because just as you saw the star being ripped apart by tidal forces and spewed all over, that's exactly what happens when galaxies collide. The galaxies are ripped apart and spew stuff all over, and that spewing stuff all over is the genesis of these stellar streams that you see there. So these are the remnants of galactic collisions from billions of years ago. Okay. And here are all the different streams that we've identified just in the last few years. This is relatively recent research. So a galaxy that appears to be populated by mostly red stars is likely. Let me bring up a poll. So look at this, and then I will bring up the poll question. I didn't program these, unfortunately. So a galaxy that appears to be populated by mostly red stars is likely A, never had blue stars, B, had blue stars that were not present but were a long time ago, C, have been around long enough for blue stars to all evolve in red main sequence stars we see, D, never contained enough gas to have blue stars develop, and E, have blue stars that are blocked by dust. We haven't talked about this, but I think it's an interesting question. Five, four, three, two, one. Okay, you actually got this right. We haven't talked about it, but blue stars are formed when blue stars can only be around for a few million years. And so, blue stars are these OB stars that are very bright and very young. An OB star can only last for maybe 10 million years at most. So when you see blue stars in a galaxy, you know that stars are being actively formed. For stars to be actively formed, you need two things. You need gas and dust and lots of it, and you also need something that collapses that gas and dust. And when you have something like the galactic disk, which has a lot of gas and dust and a lot of supernova explosions, you're going to get new star formation. And so those galaxies are going to appear blue. When you have a galaxy that has no gas and dust left over because it's done all of its star formation, you can't have blue stars. And all you're going to see is red stars. And this is the first time we mentioned it, but this is going to come up over and over again as we talk more and more about different types of galaxies. So the question is, how do the spiral arms form? We actually don't have a perfect theory of this. So the typical thought is that if you spin up, you've got some arms. The problem is the arms can't exist as you would expect. That the galaxy would spin them up, and so the center of the galaxy spins faster than the outer components of the galaxy, and so eventually the spiral you would spin it up so much that the spiral arms would disappear, as you see by this progression here. Okay, so it can't just be arms that form and just are the differential rotation creates those spiral arms. There has to be something that's actively forming these spiral arms. One way is called what they call density waves, which is really kind of the way traffic bunches up when you're on a highway, or the way the waves form. The bunch up of traffic is formed not by particular cars, so that bunch of traffic can move forward and backward, even though cars are continually moving into it and out of it. In other words, that traffic jam is an entity unto itself, independent of cars, because from 1 minute to the next, it's instantiated by a different number of cars. So I'm not going to spend a lot of time on that. And the reason why is this is one theory. There are other theories. One theory is it's just the star formation in a particular region maintains the shape of the spiral arms. The problem is we don't really have a good solid theory about star form, not so much these spiral arm formation, but how the spiral arms are an almost a uniform feature of disk galaxies. So there must be something profound that we're missing about spiral arm formation. Hurricane of doom, yes, definitely. I mean, you see this in hurricanes, where hurricanes have this differential rotation, but hurricanes are not gravitational objects, so the center of the hurricane isn't forced to rotate much faster than the outer parts of it, and so it can have a much smoother rotation curve and maintain the shape of the hurricane somewhat. Another question, not only how the spiral arms form, but what is the total mass of the Milky Way galaxy? One way we can do that is we can measure velocities using the Doppler shift. And when we measure the velocities, we would expect that the farther out you are from the Milky Way galaxy and from the galactic hub, which contains most of the stars, the galactic bulge, which contains most of the stars in the Milky Way galaxy, what we would expect is that you would orbit the Milky Way galaxy slower and slower. Okay. And in exactly the same way that Pluto goes around the sun much slower than the Earth does. And Mercury goes around the sun much faster than the Earth does. And in fact, it follows this equation. The orbital velocity goes as the square root of 1 over r. So as r increases, the orbital velocity decreases. And this equation is this dotted blue line right there. This is what we would expect. But if we map the velocities of stars going around the center of the Milky Way galaxy, instead we get this. it's relatively flat, okay? And this made no sense. This was first discovered in the 1970s, and nobody had an explanation for it. And in fact, the current explanation, let me switch here for a second. The current explanation for that is that the Milky Way Galaxy contains not just the matter we see, but matter that we don't. And this blue sphere that you see out here is where we postulate that there exists matter that weighs more than the Milky Way Galaxy itself, that contains invisible matter we call dark matter. And it's this dark matter halo that gives us the rotation curve that basically tells us that most of the mass of the Milky Way Galaxy is not contained in the center and must be contained much farther out. And that affects this rotation curve, the speed of objects going around the center of the Milky Way Galaxy. Now, I'm mentioning this briefly. We're going to spend an entire lecture on that later on in this course, because dark matter is one of the most fundamental aspects of the universe. It contains 10 times, there's 10 times more dark matter than there is matter that we can see. And we don't know what it is. It's one of the greatest mysteries of science. So there must be unobserved mass dark matter in the outreaches of the Milky Way Galaxy. Now, this brings us to the last topic about the Milky Way Galaxy, the black hole at the center of the Milky Way Galaxy. We can't see the center of the Milky Way Galaxy, at least visually, because it's obscured by gas and dust. However, when we look at it in infrared and radio, we show that stars are moving very, very rapidly. And the only way they could be moving that rapidly is they were orbiting something that was really massive, in particular, something that was the mass of 4 million suns. And because this object is so small, it has to be a black hole. It also has extremely strong magnetic fields. It's a very strong X-ray source. And this basically proves the fact that there is a 4 million solar mass black hole at the center of our galaxy. So Sam says, could it be a bunch of black holes? Actually, Sam, that is something that's been explored. And the answer is yes, it could be. There's a couple of reasons why we think that's not true. First of all, we think if you have a bunch of black holes very close to each other, their orbits would decay in a way that orbits don't normally decay. The Earth will go around the sun for 10 billion years. However, if you're really, really massive and really, very close, you will emit these gravitational waves, and those gravitational waves will remove energy from the orbit and will shrink the orbit, and eventually you collapse. And so that's one reason. The second reason is the orbits of the stars that we see going around the center of the Milky Way Galaxy would be perturbed if it was more than one black hole, and we don't see that perturbation. We also see an accretion disk.
Hiding behind the constellations Sagittarius and Scorpius is the center of our own Milky Way galaxy, over 25,000 light-years away. This patch of sky is mostly dark and visible light, shrouded by dust clouds that lie between us and the galactic center. But the infrared vision of NASA's Spitzer Space Telescope sees through the dust, showing us this strange and tumultuous region. The image spans about 5 degrees of sky, which is about half the width of your outstretched palm, but encompasses over 2,000 light-years across our galaxy's core. Infrared light at 3.6 microns, which is mostly from stars, appears blue in the Spitzer image. Dust clouds glowing at 8 and 24 microns are rendered in green and red. The stars dramatically increase in numbers towards the center, swirling around the supermassive black hole astronomers think lies at the heart of it all.
So here is a map of the orbits of those stars, that again, we had to do this with radio and with infrared, that are orbiting an unseen object that must be a supermassive black hole. Unseen because right now it's typically not eating anything. But as you can see, these stars, they move fairly quickly when they get close to it. And here you can see the orbit of one. You see how fast it is as it gets closer. It's just following Kepler's laws. And it's amazing that we can map these. These are real observations. And here's another view of those stars orbiting the supermassive black hole. That's marked in this case by a little star. So the motion of all these stars tells us there's something really weird happening. Right. Okay. I'm going to skip this video because we want to get to the first image of a black hole. Now, as he mentioned in the video, we know how stellar mass black holes form. We've talked about that in previous lectures. We don't know how supermassive black holes form. And as far as we know, all galaxies have a supermassive black hole at their center. And most of them are the order of 1 billion solar masses. Ours is only 4 million, so ours is relatively small. And we just don't have any theory. We don't even have a guess of how they form. We do know they must have formed early because when we look back 12 billion years, we still see these supermassive black holes. So there's something about the creation of the universe that really liked supermassive black holes. So what happened last year was the first time we actually got a picture of a supermassive black hole. Not in our galaxy, but in a galaxy relatively close by, M61. And here is the picture. Now, as you can see, the picture changes a little bit as we go from day to day. This here is 50 micro arc seconds. Now remember, an arc second, remember your eye can see about an arc minute. A good telescope can see, has a resolution about an arc second. The sun and the moon are about 30 arc minutes across. So a good telescope has a resolution of about 60 times better than your eye. And we can see features on the surface of the moon. We can see features on the surface of Mars and Jupiter. This telescope that we use to produce this image of this black hole has a resolution of 50 micro arc seconds, 10 to the minus 6 seconds. So as I mentioned last time, this would be equivalent to taking a quarter and moving it not to Durham, not even to Los Angeles, but to the surface of the moon and being able to see that it is a quarter. A quarter on the surface of the moon is 50 micro arc seconds across. And so the resolution of this telescope is literally beyond belief. And that's why it's taken us so long to take a photograph of a black hole. And if you take the image you saw from the movie Interstellar and you squint and really squint, you're going to get something similar to this, because that image you saw of a black hole in Interstellar was much brighter on one side than on the other. And here's a video about the telescope that took this first ever picture of black hole, and this was just last year. And that telescope wasn't the size of, the Hubble Space Telescope, which is, I think, 85 inches across. This telescope, the size of this telescope was the size of the frickin' Earth. And what it was observing was this accreting black hole, a supermassive black hole. I forget if it's a couple billion solar masses. Here's the event horizon. Here is now of course you can't see the black hole itself, but what you can see is as you saw in the movie Interstellar, the extremely hot material in the accretion disk around the black hole. And we're looking down into the black hole itself. And what's weird is that you see the material jumping up above the black hole. The material actually doesn't do that. What's happening is the black hole is warping the light that's coming from the back of it. And so that image you saw in Interstellar, the image you're seeing here, isn't the actual location of the accretion disk, it's the way it appears, because the black hole has such a strong gravitational field that it warps light. It's like a lens, as we talked about in previous things. Here's the journey to the galaxy. I mean, it doesn't look like much, but what it took to get this image is beyond belief. This is the first physical picture we have absolutely proving the existence of black holes.
You might think you've seen a black hole before, but until now, you haven't. You've seen artists' conceptions, animations, simulations. Now, after almost a decade of work, scientists from the Event Horizon Telescope project have produced the first ever actual image of a gargantuan black hole. Why did it take so long? Black holes are extremely hard to see. Light can't escape their gravity, and from an astronomical perspective, they're small. In fact, there isn't a single telescope powerful enough to see a black hole.
If you want to take a picture of something that refuses to have its picture taken, like a black hole, you need to build a special kind of telescope. So we connect radio dishes around the globe, and we synchronize them with atomic clocks. They all look at the same black hole at the same time. And that creates a virtual dish as large as the Earth itself.
8 telescopes, an international effort by hundreds of people in 20 countries. It took literally a half-ton of hard drives to store all the data.
And most importantly, it required researchers willing to collaborate across the globe. And it took funding agencies like NSF to make a long-term investment.
And today, the world sees the first direct visual evidence of a supermassive black hole at the heart of a galaxy far, far away.
Just a cute aside, they were shipping disk drives to each other because connecting them over the internet would have taken hundreds of years to move the same amount of data. We're talking about petabytes of data, and it turned out that FedEx gave a much faster delivery speed than anything that was on the network. And so I want to finish the subject of the picture of the black hole by showing you what happens if you pull back from that picture of the black hole. So here is a picture that you saw, but now we're going to pull back a little bit and see what the environment around it is. And you can see there's actually 2 black holes and a little nose and a mouth anyway. So, if you all had your mics on, you would be laughing. Could dark matter around the galaxy be a bunch of black holes? So Sam asked the question, could dark matter around the galaxy be a bunch of black holes? That the answer I'm going to give is different than the answer I would have given a year ago. A year ago, the consensus was absolutely not. And the reason why is if these black holes were very large, we would have seen them. Either they would be accreting matter or they would be producing what we call gravitational lensing events, where you can see the light being warped around them. And so really the only room left for black holes being dark matter would be that they were much smaller black holes, which mean there'd have to be a whole bunch of them. There'd have to be quintillions of these small black holes. And not only that, but we don't believe that small black holes can exist, because the only place you can create small black holes is in the creation of the universe. And small black holes would have evaporated by now through Hawking radiation. We haven't talked about that. Hawking radiation is where black holes can actually evaporate as they absorb antimatter particles. It's complicated, but basically they can evaporate, and the speed of the evaporation of black holes depends on the mass. So small black holes evaporate very quickly. Large black holes, they don't evaporate at all. Hawking radiation isn't a factor for them. So we didn't think that what we call primordial black holes could exist, and we had observational evidence that large black holes from stellar mass on up could not be the main component of dark matter. That's changed in the last 6 months. In the last 6 months, some scientists are now saying that we misinterpreted the data, that it is possible that dark matter is black holes. Most people don't think so, but it's now a source of serious debate. The effort here is generally breathtaking, a telescope the size of the Earth in our lifetime. Well, yeah, and Alex, an interesting point is that the reason they took a picture of the supermassive black hole at the center of another galaxy versus the center of our galaxy is our black hole at the center of our galaxy changes very quickly. It changes very quickly because it's small and things are whizzing around it. And the technology of just a few years ago was such that they needed to integrate data from several days to get an image. And in those several days, our black hole changes. Since then, the technology has been updated. And so the very next picture of a black hole that you will see is a picture of our black hole at the center of the Milky Way Galaxy. And there will be a movie of it because it changes so quickly. Is that God? Interesting, yes. Yeah. I'm not going to touch that one. So anyway, let's stop the lecture now, and I'm open for questions. You're welcome to turn on your mic if you like.
So I'm still a little confused on this. Why is the black hole picture brighter on the bottom?
Right. So if you remember the movie Interstellar, in the movie Interstellar, one thing was brighter on the bottom than it was on the top. And just think of the accretion disk. And the accretion disk in general is not going to be directly towards us. It's going to be tilted on one side or the other. And because of that tilt, what happens is the back side of the accretion disk is warped by the gravitational force of the black hole. So that the brightness of the backside of the accretion disk is actually going to be folded over on top of the front image of the accretion disk. And that folding over means that one side is going to be brighter than the other. As you saw with, in fact, let's just go back to that visualization. Let's see, that'd be 16. Okay. So play slideshow. There we go.
The initial impetus.
Yeah, here we go.
Holes, nor
and this isn't quite the same, but you can see how one side is much brighter than the other. Again, because that right there is the image of the back side of that accretion disk. Okay, so the tilt has brought that image up, and so we think that the image we have of the M87 supermassive black hole is tilted similarly, and it's brighter on one side because that image of the disk has been warped up front. Okay, is that clear?
Yeah, that makes sense. Thank you.
Yeah, sure. Do you have lecture recordings? I was planning on quickly going through the recordings to get a refresher. Yes, I do. They're on the YouTube channel, and if you look on the syllabus, I have the YouTube address there. Or you could just search for my name and then go to the PY123 channel. Can you get the picture of the black hole and explain the scale again? Joseph, can you just turn your mic? I'm not sure I understand.
Yeah, you just froze when you were explaining the like how it was micro arc seconds or something.
Oh, right. Okay. So So just going through resolution, your eye can see about 1 arc minute. A good telescope can see 1 arc second, which is 1/60th of an arc minute. The resolution of that image that we saw was 50 micro arc seconds. So 50 times 10 to the minus 6 arc seconds. And again, the only reason we can get that kind of resolution is we have a telescope the size of the Earth. And that resolution is the same as a quarter on the surface of the moon. So the type of resolution they have to get this image is literally beyond comprehension. I mean, no human could comprehend something that, you know, such an incredibly fine resolution.
Okay, thank you.
Sure. Would a small enough black hole absorb more cosmic radiation than it emits? So Joe, the concept of Hawking radiation is very complicated, and I just recently read that the way it's described in the public literature is just completely wrong. But one way to think of it is the way it's described in the public literature, which is not completely wrong but very misleading, is that if you have particles that pop into existence as they do all the time, virtual particles, and you have a positive mass particle and a negative mass particle that pop into existence, and the negative mass particle is swallowed by the black hole and its partner stays outside the radius of the black hole, then the black hole will lose mass and emit radiation as it loses mass, which is complicated and actually isn't correct. But the concept is that small black holes will emit radiation and they will shrink through entropy interactions at the surface. So small black holes will emit a lot more radiation than they suck in, and they will evaporate. How long does it take for black holes to form? So we think black holes form, so stellar mass black holes, where we know how they're forming, they form essentially within milliseconds, if not even quicker. Once the collapse of the core starts, nothing stops it, and it collapses on a timescale of how quickly things can fall in and free fall, and that timescale for something the size of a neutron star is the order of milliseconds, you know, 1,000th of a second. So it forms incredibly quickly. What theory for dark matter do you feel has most support? Are there theories for the end of black holes? So right now, we don't, probably the leading theory for dark matter is what's known as axions, which are a postulated form of new fundamental matter. And I am completely agnostic. I don't have an opinion because I'm not a particle physicist. And a lot of people I know who are particle physicists really don't have a favorite either. So that one of the things that's important about getting a physics degree is that you have a deep understanding of what you do not understand, which doesn't happen before you get the physics degree. And in particle physics, I just wait until the people I respect tell me which one is the best theory. The fact that the black holes as dark matter has come back from the dead in just the last few months, I find very interesting. And it's certainly a theory that anybody can understand. Whereas axions, I've tried to read articles about axions, my brain starts to explode. But, you know, it's a wait and see. So David says, will we be talking about string theory at all? Absolutely not. And the reason why is that string theory was a postulated theory that's been popular for 20 years and has not had a single shred of evidence for it, nor a single success in terms of making a prediction that you couldn't make without string theory. And so I would think at this point, most physicists think that string theory is a fad. My attitude towards string theory is the same as my attitude to other parts of physics that I'm not part of, is that I have a agnostic wait and see attitude. And when people I respect, particle physicists, are moving away from string theory, it's like, yeah, I don't know. And so that's why we don't talk about this in this intro course, is that I'm not convinced. And in fact, at this point in time, I think most physicists are not convinced that string theory is a fundamental theory of the universe. And so, you know, if we were if we were teaching an advanced physics course, sure, we'll teach you all the you know, speculative theories of the universe. But here in an intro course, what we like to do is just teach you what's pretty solid. And dark matter string theory most definitely is not solid. Other questions? Okay, black holes are a lot of fun. Other questions about what are your thoughts on white holes? So yeah, so concept of white holes is interesting. For those of you that don't know, black holes is where stuff, you can almost say that stuff leaves our universe. It leaves our universe because we can never observe them again. If you run through Einstein's equation says, well, perhaps stuff leaves our universe, it shows up someplace else. And where that someplace else is a white hole. So stuff leaves our universe, goes through a wormhole, and pops up someplace else as a white hole. So it's like this tunnel. It leaves and then it comes back out. There's nothing in Einstein's equations that prohibit that. Doesn't mean it's true. There's a lot of equations that we deal with in our day-to-day lives that have solutions that are what we call non-physical. So I think white holes are a theory that's sitting out there. Most astrophysicists know that white holes are a theoretical possibility, but I think the vast majority of astrophysicists think that it's pretty slim possibility they actually exist. You know, for example, this concept that material leaves the black hole and shows up at the white hole, but the black hole still has mass, and that's kind of curious. It still has mass, it still has a charge, it still has a rotation. Wouldn't all of those features disappear along with the matter itself? So that's kind of a puzzle. But that said, that hasn't stopped astrophysicists from looking for white holes. And the reason that astrophysicists look for white holes is if you discover a white hole, you're guaranteed a boatload of Nobel Prizes. They'll just, you know, pop them out and deliver it to you by the wheelbarrow. I mean, it would be one of the greatest discoveries ever in the history of mankind. So that's why people look for things like that, even though the chances of actually finding them are pretty slim. Any good black hole memes? The cat one is pretty solid. So are you talking about Schrodinger's cat? So Kate, tell me about this one. Yeah, me too. So, oh, right. Thank you. Yes. Yeah. Where I showed the cat meme. Yeah, there's a lot of good jokes about that. In fact, I'll bring up some of the jokes that I found recently. Hold on a sec. Let's see. Courses, talks. Okay, where is that? Okay. 16, 17. Hold on one second. Okay, yeah, here we go. So this is a cute one. There's the picture of the black hole as we get closer and closer. That's what it looks like. This is the one I showed you. Here's a low res version of the black hole, and then we get to a higher res version. And here's someone that opens their picture, gets a bunch of black holes, and they take over. And the next one's my favorite. Okay, well, any last questions before we call it a day? Okay, thank you so much, and I will see you guys on Tuesday.
Thank you.
Thank you.